All right, guys. Yeah, let me just kind of start a little bit because my topic, as you suggested, it's actually should be related to space medicine, and we all know that exposure astronauts to space flight environments such as microgravity, space radiation, well, has some kind of important medical and health implication. It's no doubts about this. Yeah, uh, and space medicine is one of the components of human physiology, which is kind of also practical component or kind of component with applied research. We concern mostly about health, medical conditions, welfare of astronauts, and development new therapies and methods to keep them, of course, healthy in space to provide performance. That is actually most important. But however, before I start to talk about space medicine, let me step back for one moment and discuss one, I believe, very important issue which actually related to this topic. And this is about space colonization, of course. Why it's important? Because, like you can see in my slide, in all culture, actually, space is something which always inspire people. And the question is that where we are going right now, how it's important this topic for us. Some of us greatest and brilliant minds on our planet are big, of course, advocates of space colonization. And every agency, including European, Chinese, Russian, and NASA, has some plans for space colonization. What actually problem is, however, what if we would be informed that in 2040 or 2060, human race will vanish due to catastrophic events? By the way, 1 week ago, it was discovered new asteroid which coming to Earth, which is actually now probably was upgraded by NASA. That probability is collision is well, very small, of course, but it was upgraded 6 times even more than 1 week ago. We don't know actually consequences of that. But problem is that leaders and politicians in different kind of countries becomes more vocal about over past several years, considering space colonization actually as a means to preserve our species in space. Of course, climate change, problem growing population, nuclear actually pollution, urgent us to take action. And you know that, as you can see in this slide, one of the greatest mind, one of them, of course, Stephen Hawking. I met him personally in Cambridge. Of course, just bringing to us some message saying that survival of human race at risk if we just kind of confined with one single planet. So we put all in one basket. Sooner or later, disasters happen. I believe it's absolutely right, and we need to be prepared to that. So we know that the space colonization question was raised a long time ago, and unfortunately, at the current time, we have some kind of problem. Just community and people on street always ask us, does space colonization lost its hold on public imagination that it was generation ago? And we should admit, and question is, like Eric Anderson, for example, actually many times in his presentation mentioned that yes, unfortunately, there is every reason to people to be disappointed with this. Yeah, and what actually a problem is that public perception of living in space in generally based, of course, on TV, sci-fi, Star Trek, generation ships, you know, all of this, yeah, where gravity, artificial gravity and jet propulsion, you can deliver you to any kind of planet in a matter of days. But unfortunately, real world difficulties and to expand in space more complex than presented in this science fiction. And we all know that. We know that actually line where it's fiction and where is reality. And we need to admit that people not thinking, some people, most of the people, not thinking much about space. They are concerned primarily, of course, about their life, about economy, which immediately affects them. The foreign policy. Others believe that actually space exploration is hundreds, millions, and billions of dollars. That's too expensive. And probably, of course, they may be right. For example, if you know Apollo, which happened a long time ago, would cost in 2012 or today money, 2013 money, like 10 billions per astronaut on the moon for a few hours or one day. Of course, it's very, very big money. And we agree that this matter of order, its or magnitude, is do matter. However, should we admit that, for example, in America in 2010 or 13, NASA budget was much less than Americans spent for pizza. And during these years, for example, between 2000 and 2013, they spent like $88 billion only for tobacco, 97 billions for alcohol, and the most important, 586 billions for gambling. So we understand that, yes, if we can spend this money for such things, we can afford space exploration. So, and now just why we disappoint? Because look, in last century, let's say in 1960s, people were so enthusiastic. Me personally, when I was just 5 years old and I was listening Sputnik with my father, I was 100% sure that in 2000, whatever year, we will be on the Mars. Unfortunately, not yet. And you can see, for example, as presented in this slide, at 2077, it's absolutely, I mean, huge, unbelievable enthusiasm when people prepare detailed plan for integration in space, for space settlement, like hundreds of pages, very, very serious. In particular here, NASA Ames Center at that time participate in this kind of space settlement project. Also, at that time, it was projects for lunar, for example, base. You can see on the right Biosphere 1 and Biosphere 2, which Americans spent like 100 millions and 1.2 billions, which completely close ecological loop, which model settlement on some kind of planet. You can see also asteroid actually project, which was kind of described how we can actually use asteroid to arrange a settlement. And of course, students participate in so famous Space City. And Space City is just kind of course, amazing project, which I was kind of impressed even at that time. You can see, and people should live in this kind of ring-shaped tube, which connected to actually with 6 roads to deck, and it's approximately like 15 meters in diameter and 1 mile in diameter. I mean, in cross section, approximately 20 meters, and there should be 1 mile in diameter. Believe me, people really spent a lot of time actually making such kind of projects. And even now, when we focus mostly on Mars, you can see in the literature that a lot of books which kind of in details discuss what we should do, how we should go and colonize a planet which is most probably reasonable to explore for purpose of colonization. Unfortunately, all of these kind of questions are not so simple. And everybody knows that a lot unaddressed questions like moral, ethical, which is actually really slowed down our efforts in space colonization. And we should understand that reality, it's not like here I present so rosy as a dream. And biggest problem we actually face it is humans evolutionarily adapted to live under this condition of low gravity. We in some kind of gravitational hole on the bottom. It's like trap. And get out of that, it requires a lot of effort, energy, and of course, it's very expensive at a certain time. So what else we expect? Of course, unbelievable alteration in human physiology. And here, of course, we all know that, for example, as soon as you place man in space, we have a lot of problems. Now, this question is it just kind of problem with temporary? Can we handle this? And this question still actually already in the process of answering. Already 2 decades, we rounding around globe and trying to figure out actually how we can handle these physiological problems. First of all, you know that astronauts, as soon as they place it in microgravity, they immediately actually have change in blood volume, like 25%. Immediately after that, heart has problem to actually pump of this less blood volume, and the heart has atrophy. You know, it's immediately if it said it has atrophy, delivery oxygen to brain, it's significantly restricted. Here you have problem with dizziness. Most important, of course, yeah, if you analyze all this immunology, for example, it's unbelievable now that it's absolutely weak. Its consequences very dramatic. Of course, what immediately appears, it's a bone and muscle degradation. It's so significant. And if you take a look at the next slide, for example, we can see how different kind of physiological actually markers change. And you can know that most change occur during like so-called transitional period, when it's deviated from the set point and becomes near clinical horizon. But of course, it's dangerous. Yeah, and this is actually a very important period for human physiology, like probably like 1 month, or less even. But then start to decline and go to near normal actually conditions. Only one thing which actually you can see from this slide uh, actually changes uh, gradually, always increasing. It's only bone and muscle metabolism and also radiation. This is a linear increase. And you can see here a scale from 1 to 6 months. And you can extrapolate it and say what happened in 1 year. It certainly crossed a clinical horizon. So radiation is accumulated dose. It's inevitable. You cannot do nothing. It's like a bullet. Of course, you can protect. And now this is actually what we want to discuss, these two actually topics, which I believe inevitable. We need to address actually these issues. Let's just see what happened with status of bone loss. Yeah, nothing much changed since our first steps in space. And we know that during crew members, yeah, during 12 months mission in Soviet, for example, Mir spacecraft, International Space Station, experienced significant loss in bone. They carry them. And you can see 125, 162 days. And even now we have, of course, countermeasure. And what is that? Of course, degradation, as you can see, is just microtomography in bone density. It's on the left before and right after flight. Density decreased dramatically. And on the right, you can see the figure which hypothesizes changes in bone if we take mission to Mars. And you can see, for example, that over flight, it will lose like 10%. And then on a Martian surface, it's much less, of course, yeah, but then return flight. But overall changes so dramatical that even at the end of surface mission, yeah, we will experience so big problem that probably even astronauts cannot accommodate and return to the Earth. Because as you know, for example, recovery of bone after 4 months actually, or 10 months in space require 2 or 3 years to return to normal. And after, let's say, 360 days or 500 days on space, it probably becomes irreversible. And that is most important, whether astronauts actually can return and live, continue to live on Earth, or it will be one-way street. It's important, it's a very ethical issue whether we should send, and we discuss in literature, our center director addresses this question many times, whether we ready actually to say to public that we can send astronauts in one way to Mars. And probably now we cannot do this. And NASA doing everything to actually provide safety astronauts for round trip. So what kind of countermeasure we have actually for bone muscle loss? Only just kind of like 2 years ago, it was discovered some protein which is called, of course, people use normally a list of different kind of medication, pharmaceuticals. Yeah, most of them known is bisphosphonate. Which astronauts taking actually, which prevent bone loss, but unfortunately they have severe side effects. And we're looking for some kind of medication which would be less toxic and it has some kind of preventive effect for bone loss. Like I said, in this case, recently they found sclerostin, which has a very important role in bone metabolism. And sclerostin problem, it's of course is great interest or potential as a potential target for therapeutics to decide some kind of medication. It's a very small protein, but unfortunately, this is biopharmaceuticals. Yeah. Next slide, which I actually copy from Amgen, which we start to collaborate on this issue, actually, which already tested, Amgen already in collaboration with the European company from USD Pharma and NASA, tested this actually drug on a mice. 30 mice, as you can see, was treated, pre-treated before flight with the one injection of this drug. And what we know after that, that on the plot you can see on the ground, for example, it's normal. After flight 1 month, yeah, bone density dropped 6%. But if you pre-treat mice with such kind of medication, you can see increase very substantially, 12%, and becomes even more than it was in the control, ground control. It's very promising, actually, drug, which now Amgen, yes, it's already in third clinical trial, and it's ready to be released to public. So now about radiation, it's another issue. As soon as we just kind of going out of magnetic field of the Earth, we immediately exposed to such kind of radiation which we never yet experienced, because so far we just kind of in orbital flight when we protected magnetic field, you know, it's not much radiation, but still significant. I will show you data. But as soon as you go out magnetic field, you can see that from cosmic radiation, you will get, for example, as presented here, like 4 protons for square centimeter every second, or 0.4 helium, it's or high Z actually particles, it's ions. And these ions, it's not proton, which you can stop. Like they like bullet. You cannot even just kind of prevent from this radiation with shielding. And point is that each cell which has nuclear with DNA, of course, yeah, approximately size like 100 micrometers, yeah, each proton once every 3 days. Every just iron, for example, particle once per year. And you know, astronauts in our early flights was always experience some flashing. They report that for some reason we see in our eyes some flashing. What happened is just, of course, it's high particle radiation passing through the brain and creates this effect like flash. Radiation, of course, recently was updated. Curiosity mission. And that actually very actually becomes important, because before, and in the graph you can see, we expect that different kind of exposure. Yeah, and you can see that, for example, cosmic radiation average annual level. You can see that annual level exposure for professionals from CT scan in the hospitals and the lunar mission. 6 months on the AES, but what's most remarkable, 6 months transit to Mars, it's 600 more. And most important, note that scale is logarithmic, it's not linear. And this, what we're getting now in 6 months, half a year International Space Station, it's significantly higher that we have Walker, radiation Walker limit. But on the Mars, we expect even 6 times more. It's approximately 600, I guess, 32 millisieverts. What's important on the bottom of actually this slide, you can see cancer risk development or cancer risk death. And you can see that risk increase even at International Space Station we have very high. It's like a coefficient with 1. And lunar and Mars becomes already in the red category. You please know that, of course, it's just factor of age. And on the plot, you can see that, of course, in young age, coefficient with multiply radiation actually damage, it's very high. And it's developed some kind of plateau in the range 35 to 60. This is why most of the astronauts, yeah, which we have at NASA, is kind of in such kind range of age. And of course, exposure, damaging effect of radiation much less when people become older. Well, but we don't want old astronauts, of course. Yeah. So now, what we have to protect against radiation? Of course, first it's shielding. And shielding, it's kind of material. We have problem with that because it's very high payload cost to deliver. Of course, you can deliver lead, for example, over there. What we have in International Space Station, 15 centimeters of polyethylene. And it's enough because it's still orbital flight and we protect it. What will be in the Mars mission, we not know yet. And especially after this new data from June 2013 from Curiosity, when just tell that it's much higher radiation than we expected. Now, second category, of course, is biological protection. And biological protection, we're working right now in my laboratory, particularly working on development new radio protectors. And of course, it's second front of protection because you're already exposed to radiation, nothing you can do, you have damage, and you need to manage this. Of course, we have huge list of countermeasures, yeah, mostly pharmacological, which already on the market since Second World War. But problem is that all of this list, yeah, or the efficacy very low, or toxic effect at the dose or concentration dose when it becomes helpful, it's a lot of serious side effects. Only recently, probably I just already reported to you last year, it was kind of new development with actually Cleveland Biolab company, which developed new radio protector, which looks like very, very promising. Even in Fukushima in Japan, these catastrophic events, actually, they request this drug, which not yet FDA approved. And idea is that, you know, they consider pathogens, normal bacteria which has pili, and this pili just made it from flagellin, some protein with flagellin. So this bacteria to cause inflammation interact with this pili with so-called toll-like receptor number 5. You can see schematically presented over here. What these scientists did, they obtained this fragment of flagellin which interact directly with this receptor. And so they developed lead, so-called lead compound. And they start to test on the animals, and you can see on this plot on the B and D, actually survival of animals, monkeys, after exposure to different doses, a little dose of radiation without injection and with injection of this drug. And you can see that even at 100 grays, when 100%, well, 90% of rats died in the next 30 days. For example, they're absolutely perfect after injection. So this very, very promising drug, and now it's in third clinical trial. And the US government actually spent like $200 million granting this laboratory for development of this pharmaceuticals. Another one promising actually countermeasure against radiation is based on so-called elongation factor of 2. And you know that polypeptide change of all proteins we synthesize in our body actually on ribosome actually regulated by different factors like initiation, translation factor, elongation factor, and the termination factor. So scientists found that elongation factor 2 kinase, which inhibit, for example, this kinase, may be very good potential pharmaceutical or therapeutic product. And they, for example, in this picture, which I take from my friend, Dr. Alex Rizanov from Rutgers University, they inject, you can see 2 mice. One of them black hair, another very gray hair. And the gray hair, this kind of mice was exposed to sublethal dose radiation, approximately 7 grays. And the black hair mice was also exposed, but pre-injected with this elongation factor peptide. And you can see that the effect is dramatical. You can see that, well, it's one of the criteria, gray hair, what actually impact immediately, visual impact of radiation on the mice. And then you can, of course, confirm this and validate with the survivability of these mice. Now, question which probably, I put it as a text in reality because what I want to say here, what actually our conclusion? If we have such kind of low gravity impact on bone and muscles, and we have such kind of radiation which we kind of barely can handle, can we actually consider question adaptation in space environment? We know all that what we mean adaptation. Normally in all evolution adaptation, we know it through the mutations, right? Which actually could be selected by environment. Whether they fit, then species survive. And this mutation change organism and increase probability, of course, of survival. However, it's required generations to adapt to space. For one living species, not much you can handle. For each specific species, for example, with a time life, it's practically impossible to accumulate such kind of mutations, which would, for example, would allow you, let's say, to fly. It's require many, many generations. Even an E. coli, simple bacterial system, they show that very substantial changes which could accumulate and adapt E. coli to changes environment require approximately 5,000 generations. Therefore, what would they expect? How cosmonaut can adapt to space environment? Of course, they cannot, because only just kind of one way, if they expose without protection to such kind of damaging factor, they only have way to die. And it turns out that environmental factors of this weightlessness and the harmful radiation becomes very, very important. And we don't know at this point whether we have countermeasure. Second one, of course, if we consider space colonization, it's automatically question which we should address. It's reproduction. At such level of radiation which we have outside of magnetic field of Earth, many experiments was done on the ground, of course, yeah, shows that reproduction is not possible. And even just experiments which mimic closely space radiation on a monkey, for example, primates, yeah, show that even if it would be in orbital flight, there is some complication and second phase of pregnancy. So what we have, exposure to DNA, which damage embryon, and we don't know who will be born. And that's a very important issue. Of course, we can just consider fertilization as I present on the top of this slide. We should keep egg in some special protected and lead container or whatever, and being under safe condition, we can, of course, to reproduce human species. But in space, probably not. So third issue, which is also important, yeah, I believe it's psychological effect living in space. And you know this is not simple. Of course, people practice in caves, in Arctics, in close environments to see what would be impact of this actually close environment on a psychological. Of course, it's a lot of stress. And you know, it as presented in here recently, last one, Mars 500, when a team of international team of mimic crew members on the way to Mars on the surface and return back. And they kind of mimic all activities which we expect from astronauts on this trip to Mars. And you know that it's not actually first such kind of project. It was before, I guess, in 2008, and it was completed with broken nose, some kind of it's a problem of interaction or communication, and was interrupted. So this was actually second, if not third attempt, when team member was very precisely selected. Now, when we just kind of put all these issues of medicine, what we expect, how we care about human physiology, I would like to kind of refer you to HRP program at NASA, which manage most of the space medicine related issues. Of course, it's organization which was created specifically actually to address questions of human health, performance, and focusing on some kind of basic comparison research. Of course, goal of that to understand actually consequences of space flight on human body and develop some kind of approach and methods how we can handle this. This is actually very, just to give you ideas, huge organization with such kind of infrastructure. Of course, HRP program related directly to chief medical officer. It's actually flight surgeon group which monitor performance, behavior, state of astronauts, and participate first of all in selection of astronauts. They monitor it during flight and after flight. And human research actually program directly report actually to this chief medical office. Human research program itself has different elements, like you see on the bottom. It's behavioral health, human health countermeasure, space human factors, space radiation, and external exploration medical capability. What's important, yes, we have kind of collaboration and we participate in this program. Particularly my laboratory, we just actually involved in so-called pharmacology. We develop and trying to develop and screen and evaluate different kind of countermeasures, particularly pharmaceutical countermeasure, which would protect astronauts, for example, from actually impact of damaging environmental factors like low gravity, of course, first, and radiation. And you can see from this slide that it's a huge collaboration with different countries, ESA, Chinese, Russian, Roscosmos, and of course, inside of it's mostly important, it's NIH, Department of Defense, Department of Energy, and NSBR, which is actually NASA Space Biology Research Institute. What actually, it's different categories which cover HRP program. It's like I said, it's medical capability countermeasure. You can see from this actually list. What is important, that strategy is very simple. This program accumulates first of all evidence from flight. They monitor, they collect all this data, yeah, and then estimate risk of exposure to different factors. As soon as they know, for example, risk, how much, for example, percentage of bone loss per month, like 1.7% per month during orbital flight, they immediately estimate risk. And as soon as it will be, what should be actually, they can see gaps between current situation and risk which could be faced. Immediately develop task. What should be do to eliminate or reduce or mitigate this risk? And after that, of course, it's immediately we have some kind of program, integrated research plan, which move to solicitation, for example, to give money to different universities or program money to NASA research scientists to actually cover, to actually reduce this risk. Of course, it's immediately deliverable and cycle is closed. And finally, of course, after all of this, of course, we need to compare to standards. And standards, for example, it's very well established for radiation, for example, that it should not be more than some percentage. For muscle loss, it could not be more than 70%, or bone and cardiovascular standards well exposed. And after that, we just in HRP actually prepare such kind of chart which actually demonstrate readiness, for example, to different mission according to different categories. For example, here, human health countermeasure, HHC, you can see a different mission, orbital mission, lunar mission, and Mars mission. And you can see different color when it's acceptable in green, when it's not acceptable and in process yet, and red, which mostly for Mars missions. And after that, we just put it in a kind of a timetable, and we can see progress to a deadline when to starting some mission, it would be already completed. I will give you a couple examples over last year. For example, every year we have some kind of medical problems in International Space Station which addressed. For example, one of the last one was found that all practically astronauts, for some reason, have changes in vision. Sometimes it's good, it's improved. Sometimes it's bad, it just drops significantly. And problem, it was really severe because it's around 75% of astronauts experience such kind of medical problem. And it was addressed, and it was found that it's, of course, it's high intracranial pressure, which is responsible, which increase pressure and squeeze eyeball. So vision changed. And that was problem at the beginning, because now people trying to think how we can compensate, because what is actually intracranial pressure? Why? How we can manage this? Because it's very dangerous, not only for vision, actually for eyes, but also for brain. And in this picture, I specifically present you actually a very unusual presentation of brain, when brain was actually filled with plastic emulsion, and so rest tissue was removed, and what you see, it's blood vessels in a brain. And you can see that it's huge network of connection. Now just you're wondering probably why people have a stroke. Of course, probability of stroke could be high, but problem is that at high actually intracranial pressure, pressure, we have a lot of problems. First of such problem, what is actually reason for this intracranial pressure? And people now believe, and we just recently submitted grant to NASA, which actually address issue of blood-brain barrier. And blood-brain barrier is a very important kind of barrier which actually separate brain from a bloodstream. And so only some molecules allowed to pass through that blood-brain barrier, and blood-brain created endothelial cells, which tightly, as you can see on the picture below, connected to each other, not allowed to pass, for example, for some pathogens, for example, like bacteria or whatever. But under some certain conditions, yeah, medical conditions, and especially we believe on the spaceflight environment, we have some kind of problem. Space, low gravity, well, increased pressure, redistribution of body fluid, jeopardize integrity of blood-brain barrier. And so some infection can come, and we have such kind of consequences, which so far we just actually can manage as a problem with the eyes.